Hi everybody. So today we're going to be reviewing Physics 341, which is our classical mechanics class. So let's just think back a little bit about to what we know about classical mechanics. So in 115, you did a lot of work with kinematics equations. If you probably remember things like a kinematics equation that looks like this. Let's say x equals x naught plus v naught t plus 1/2 a t squared. Yeah, that's an a, not a g. Okay. Let me erase that. That's just way too messy. Okay, there we go. All right. Now, this is a kinematic equation that you may have memorized, or you don't have it on an equation sheet when you need it. And I hope that you remember from 341 where this comes from, right? This comes from a very specific differential equation, and that is Newton's second law. Again, you might be a while since you took 341, but Newton's second law is a differential equation. Okay, so let's write down Newton's second law. All right, and remember, it's this sum of all the forces, right, is equal to the mass of the particle times the acceleration. And of course, the force and the acceleration are both vectors, right? So where does this thing come from out of this? Okay, well, let's back up a little. We are going to look at, as an example here, just a constant acceleration particle. Okay, so for instance, a particle falling near the surface of the Earth, being subjected to gravity and falling, okay? And let's say that's the only force on it, so there's no friction or air resistance or anything like that. Then we would have a constant acceleration. Or in many physics problems that you have in 115, they say a car is uniformly accelerating from rest to its final speed, right? So they'll say uniformly acceleration. So this means that the acceleration does not vary with either distance or time. Okay, so what does this mean? So we're going to go constant, or like, how do we deal with that? Acceleration. Okay, which means that A, the vector A, so all components of A, the X, the Y, and Z components of A, all are not functions of position, X, Y, Z, or time, okay? They're just a number. Well, there might be three components of them, right? Because you might be accelerating in all three dimensions, but it's just a number. It's not a function of X, Y, and Z and T. So they are constant, right? So constant acceleration. So in that case, let's write down what Newton's law looks like. Let's get our pink back. So we're going to turn it around here. We're going to say MA, again, this A is constant, but could be X, in the X direction, Y direction, and Z direction. I'm gonna make it only one dimension in a second, but I'm just gonna say it could be all three. And equal to the sum of the forces. Okay. Okay. Okay, so we have to figure out what force we're talking about. I'm going to deal with that in a second, but I'm just going to write down these equations. Oops, I forgot my vector sign. So this is actually three equations, right? Okay, so let's look at mass times the x component of the constant acceleration. That, of course, is going to be the sum of the forces in the x direction, right? And we get a second equation, the sum of the forces in the, m times the acceleration in the y direction is going to be the sum of the forces in the y direction, and m times the acceleration in the z direction will be sum of the forces in the z direction. Okay, so Newton's equation, Newton's second law here, is actually three equations. Okay, and I said it's differential equations, but I don't see any derivatives up here. But let's write them down in their derivative form, because we know that the acceleration is the second time derivative of the position, right? In other words, right, it's the first time derivative of the velocity and the second time derivative of the position. So let's write them down again one more time. as the differential equations that they really are. Okay, so the x acceleration here is the second time derivative of x with respect to t. Okay, and that's going to be, of course, the sum of the forces in the x direction. And then we do the same thing with a y, second time derivative with respect to y. And that, of course, will be the sum of the forces in the y direction. And we'll do the z acceleration is the second time derivative of the position in z. And that's going to be the sum of the forces in the z direction. Okay, so we're going to pick a couple of these and work with them. For instance, let's think about a projectile. Okay, so you know the drill for projectiles. Hopefully you remember, we have a situation here, we have x and we have y, and we have, a cannon or something here. That's just a little cannon. And it's going to lob a ball into the air, and we get this nice sort of parabolic, I can't draw, I'm so sorry, a trajectory of the cannonball. Right? And if we think about this situation, we know what the forces are. So what are the forces in this situation? We have the force in the y direction is going to be minus g, right? Because here's my positive y, and g points straight down. All right. So it'll be a downward force like this. mg. Sorry, gm. Let me get that, because that's just going to make everybody nuts. So mg, right? So straight down. In the x direction, we have no force acting, because we're not going to take into account any, air resistance or, spin or crazy stuff like that. And of course, in the z direction, we also have a 0. And the z direction here, if you want to visualize that, it's coming out like a little arrowhead pointing out of the screen here, pointing towards you. And there's no force in that direction, right? We're not going to take into account anything like I said, we're in 2 dimensions really, but I'm going to keep all of them. All right. So now we know what to write on this side of the equation for the forces. So in the x direction, the sum of the forces is 0. In the y direction, the sum of the forces is minus mg. And in this direction, the sum of the forces is 0. And so this gives us the differential equations that look like this. M d squared x dt squared equals 0. And m d squared x, oops, that's a y, d squared y dt squared equal minus mg. And last but not least, m d squared z dt squared equals 0. Now, I know that in 115 we never dealt with z, but I just want to be complete here, right? No one even bothered with z, because we were always treating projectiles as 2D motion because we can. So you can imagine that if you shot a cannon, in all kinds of different directions, that motion is still 2D in the plane where you shot the cannon from, right? So in this plane. So you can always treat it as 2D, but I'm just being complete. Okay. All right. So let's work with all of these. Let's see what we can do to solve them. So I'm going to do this one first, the x direction. And I'm going to get my solution here in orange. Okay. So we're going to look at the x direction solution. Okay. And I'm going to write down the differential equation. So m d squared x dt squared, and that's equal to 0. Now, of course, I can get rid of the m, right? Because I could just divide by m. So this really gives me d squared x dt squared equals 0. All right. Now, this is second order differential equation. In this case, it's super easy to convert this into a first order, because I know that the first derivative with respect to time of the velocity is the acceleration, right? So this is the acceleration, remember, right? This is a sub x. Okay. All right. So I'm going to write that down. So I'm going to convert this to a dv sub x dt, okay, because that's a first order differential equation, super easy to solve. And I'm going to do separation of variables here. So I'm going to say dv sub x is equal to dv dt is equal to 0, right? Oops, I messed that up. Don't even need separation of variables here, right? Okay, so this is telling me, right? What is it telling me? If something's derivative with respect to time is 0, it tells me that that object, v sub x, is a constant in time, right? So I can write that down. V sub x equal constant, right? So V sub x is not going to change. And you probably remember that from projectile motion, right? That in the x direction, there's no force acting. So if that thing wasn't falling, it would just go forever in the x direction, right? But it's actually falling. It's going to hit the ground at some point, so it's going to stop it from going anywhere. But if somehow it was not falling, it would just keep going in the x direction at a constant velocity. And we already know what we call that constant velocity. It's the initial velocity in the x direction, right? Usually we write, let me get a little yellow here to get my thing here. Usually, of course, we have, here's v, right, the vector v, and there's usually some angle here, theta, and so v0 sub x is just going to be v0, right, times the cosine of theta. Hopefully that's familiar. Okay, but it's a constant. It doesn't do anything, right? Okay. What about x? We haven't gotten x. We got v sub x, but let's get x. Well, we do know that, of course, v sub x, oh, I'm still in yellow. I need to be in orange. Okay, so v sub x, I'll go over this. Here we go. Right. V sub x is dx dt. So turn that around. Dx dt equals v0 x. And so v0 x. So now I can write in what I have here, which is v0 cosine. Give me 1 second here. Okay, that doesn't really look like theta. Let me fix that. Okay. And let's fix this whole thing. Okay. All right. So again, this is just v0x is this thing. v0x cosine of theta. So that's the differential equation. So we do solve that by separating variables, right? So we put dx on one side, and we put v0 cosine of theta on the other side with the dt, and we integrate both sides. Okay. Now on this side, we just get x, right? And on this side, this is a constant, that's a constant, that's a constant, right? We just get v0 cosine of theta t. Okay, so so this should be familiar. This probably looks, you've seen this before in your 115 class for the trajectory in the x direction, right? So this is x as a function of t, right? That's what we solve differential equation to get. And you can see it's just a constant, it's motion with a constant velocity. Okay, let's do the y direction. Okay, let me get a new layer. And again, if I'm going too fast for you, of course, that's the beauty of video, you can pause it. Okay, let's do the y direction. Okay, remember our differential equation in that case was m d squared y dt squared is equal to minus mg, okay? So here we can get rid of the m's on both sides and we end up with this differential equation is equal to minus g. Okay, again, we're going to use our trick where we know that the first derivative of the velocity in the y direction, right, is the same as this, right? The same as the second derivative of the position. So I'm going to write that as dv sub y dt is equal to minus g. Okay, and now I can use separation of variables here. So I say dvy is equal to minus gt, and I dt. Oh, what did I just do? Wow, there's no t. Nope. Okay, minus g dt, and we integrate both sides. And here we get v of y, right, Oh, and I forgot something on the other page. So let me go back to the other one. Give me a second. I just completely like spaced that. That wasn't good. When I integrate this here, I need a constant, right? So this should be plus c, right? But if we look, what happens when t is equal to 0? This term goes away, and x becomes x naught, the initial position, right? Here I drew it as if x naught is 0, but that's not necessarily, doesn't need to be the case. So I better be more clear and now write this down as v0 cosine theta t plus x naught. That's a little better. Okay. Very often we were shooting projectiles in 115 from y equals 0, x equals 0, right? But here, you know, that's not necessarily the case. Okay, let's go back to our other layer, keep going. All right, so here we have Vy and is equal to minus GT, right? I just integrated, plus a constant. Well, what's that constant going to be? Well, it's going to be the initial velocity, right? Because if I put t equals 0 here, I get Vy0, so the initial velocity in the y direction, right? Okay, so this means this constant is just the initial y velocity. And again, if we go back and look at our plot here, right, that's going to be that should be V0. V0 sine of theta. Go back here. Okay. And so I'm going to write this as minus GT plus V0y minus GT here plus V0 sine of theta. Great. Okay, but we're not done yet because we still don't have y as a function of t. But I know that Vy is dy dt. So I'll write that over here again. Dy dt is equal to all of this because all of this is Vy. So we get minus gt plus V0 sine of theta, and we'll use separation of variables again. So dy is minus gt plus V0 sine theta, and all of this is times dt. And I got to integrate both sides. There we go. Integrate both sides. Here we get y, and over here, right, we get two integrals, so I'll separate them. So we get minus g is a constant, right? T dt, that's not a y, that's a g. T dt, and then plus V0 sine theta is a constant. And then we get the integral dt. All right, this gives us minus g t squared over 2, and then plus V0 sine of theta t, and then we need a constant of integration. And again, if you look, at t equals 0, this will be gone and this will be gone, and this is going to be the initial y, which most of the time is 0, but you know, we might as well put it in. So we know this is going to be minus 1/2 gt squared, which should be very familiar, plus V0 sine of theta times t plus y naught, right? Oh, yeah. And I think I made a mistake on the other thing. Anyway, okay. So here, let me go back for a second because I think I made a mistake there. Let me just check. Yeah, that's fine. V0. I just didn't have a V0 up here. There we go. We got a button on there. All right. Let's go back. Okay. All right. So this should look familiar, right, for your projectile equations. Go look them up on the web, right? It'll remind yourself that these are the equations that you learned for projectile motions. This was y, and remember x was, what was it? V0 cosine of theta times t plus x naught, right? And then for z, right, that's going to be exactly the same as the solution for x. Okay, so let's just write it down. So z is equal to the velocity, the initial velocity in the z direction, right, times t plus initial z. Now, in the picture that I drew back here, there is no velocity in the z direction, right? It's all in the x and y, right? So it's planar. Like I said, all projectile motion is planar unless you have something else going on, like spin of the cannonball or air resistance or whatever, right? Or a wind or something. So I really don't need the z equation, but just pointing it out. All right, so let's go back here. And this would be it. If we had some kind of initial z direction and there was no force in the z direction, it would look like this. Anyway, okay. So the whole point here is to show you that the equations that you know and love from 115, like for projectile motion, come from a differential equation. And in fact, there are 3 differential equations, right? Because there are 3 components to Newton's second law. So this is a differential equation that gets you all the kinematic equations. Now, if you have a more complicated system, so for instance, if you have a situation here, let's see, where you have, suppose you have, lots of other forces. Okay, so you might have air drag. You might take into account the fact that g changes a little bit depending on height, right? Because you're farther away from the center of the planet. Take into account changes in g. G with height. Okay. Before you accept, yeah, I can't spell. Okay. Let's put that better. There we go. I think it's I-E. Yeah. That look better? Anyway, terrible speller. Okay. So take into account kind of changes in G with height. There could be all kinds of, spin. So you can have forces due to spin forces, right? You can have Coriolis forces. Okay, all kinds of other forces. All you need to do in Newton's formulation is execute this differential equation. M d squared x dt squared. Oops. Let's be, well, actually, let's be a little bit more general. Md squared, some position vector. I'll tell you what, we'll just write all 3 down. D squared x dt squared is equal to sum of all the forces that act in the x direction, right? So maybe the air drag is somewhat in the x direction, and some Coriolis forces, some spin forces, and you have to tally them all up in here. And you have the second one, d squared y dt squared is equal to this. Tally up all the forces in the y direction, and d squared z dt squared. You would tally up all the forces in the z direction, right? So you have 3 equations here. But once you get to the point where you have a differential equation to solve, right, you can either crank through it on paper like we just did, okay? Most of the time, if you have complicated forces, that's not going to be possible, okay? So in general, what you do is stick it into a computer and numerically integrate to solve the differential equation, okay? So from here, right, these are called the equations of motion. Or EOM. These are the EOMs, right? Once you're there, you're done, right? You really are. Because yes, you might have to go to a computer and like crank through a numerical solution to your differential equation. But a lot of the heavy lifting has been done because you have the form of the differential equation to solve. You also need initial conditions, okay? But those are something that are dependent on the problem that you're doing. All right. Now, so what I'm trying to get across here is that as soon as you have the differential equation written down, right? So you've tallied all your forces, you've written it all down. All you have to do is solve that equation, which is pretty simple given that you can also use a computer. Okay. Now, not always true. Just to give you a caveat, if you're solving for multiple bodies, right, that are interacting with each other, it is not simple, even with a computer. But never mind that. Let's just talk about one particle. Okay. So getting to that equation of motion is the goal, right? Getting to the point where you've got all the forces tallied, and then you can write down the differential equation is the goal. Because solving it is kind of like, whatever, I can do that. Give it to your grad student. Okay. But Newton's second law, although super awesome, is also a pain in the butt because it deals with forces. And as we see, it's 3 equations, not 1, right? And that can make life a little difficult. Forces are difficult to deal with, right? So think about getting the components of, I don't know, Coriolis forces, right? In 3 dimensions, right? It's difficult to actually figure out what the forces are on your system. So that's the hard part of getting to the equation of motion in using Newton's second law. So if you remember from 341, we introduced a whole new framework, and that framework is the framework that is used in all theoretical physics. People, after 115, kind of don't deal with forces anymore. Maybe if you're an engineer, you'll deal with forces. I'm assuming you will, to do things like build bridges, et cetera. But in sort of theoretical physics, this force formulation is not the most used at all. We use something else that is formulated in terms of energies, kinetic energy, potential energy, in a very similar way to what is used in quantum mechanics. So if you remember, in quantum mechanics, we use something called the Hamiltonian, which is the total energy operator. It has a potential energy, it has a kinetic energy term, and you have this one beautiful equation that's the Schrodinger equation, which is the Hamiltonian operator applied to your wave function in an eigenvalue, eigenvector equation, okay? And that formulation only has energies. Notice there's no forces in the Schrodinger equation, right? So we don't write down forces. Even when we solve the Schrodinger equation for something like an electron in a hydrogen atom, of course that electron is feeling forces due to the proton, well, a force due to the proton, right? That's an electric force, but we don't write down that force, right? We use the potential energy due to that proton. That's what we use, right? The potential energy between the electron and the proton is what we use. So we write down everything in terms of energies, and this is a much more fundamental thing that is used in physics, this idea of writing everything in terms of energies instead of forces. Okay. It also has a big advantage in that energies are not vectors, right? No vector nature, don't worry about that, right? We don't have to add things vectorially, none of that stuff. It's just scalars, right? Kinetic energy is a scalar. Potential energy is a scalar, not a vector. So this formulation in terms of energies is much more fundamental. And we did it in 341, and it's called the Lagrangian formulation. And the equations that are equivalent to Newton's second law are called the Lagrange's equations. So let's look at an example of that. Give me a second here to get it loaded. All right, so let's take a look at that. Let's get a new layer. Again, pause the video if you need to catch up. All right, so again, like I said, getting to the equation of motion is what we need to do. So if you remember from 341, we looked at something called the Lagrangian. So let me get my pink color right. So Lagrangian dynamics is what we're looking at now. Dynamics. Okay. Give me a second. I just had a little error, so we will pause for a second and come back. Okay, so we're looking at Lagrangian dynamics, and this is the replacement for Newton's second law, differential equation, in terms of only energies. All right, so we're going to look at the same thing. We're going to look at projectile motion, but we're going to write down this in terms of Lagrangian dynamics. So what is this Lagrangian, if you recall from our work in 241? The Lagrangian is this object that is the comprised of the kinetic energy of a particle, and then minus the potential energy. I'm going to call that U. So this is the potential energy. Okay. All right. A second here. I gotta fix this layer. Okay. So it's the kinetic energy minus the potential energy. All right. So let's figure out what that is for our system, which is a projectile motion. And let's just stick to 2 dimensions, all right? We don't need the Z. Okay, all right. So we have motion in the x direction, okay? So we have motion in the x direction, right? When we shoot the projectile. And we have motion in the y direction as well, right? Direction. Okay, so that means there's going to be a kinetic energy term for each of those. All right, now, if you remember, when we write down Lagrangian, let me write down the kinetic energy first. When we write down the kinetic energy, we usually use the dot to mean time derivative. So we'll say, okay, there's motion in the x direction, that's going to be 1/2 mx dot squared, which is just shorthand for the time derivative of the, in the x direction with, right, the time derivative of x, okay. So in other words, x dot is just shorthand for dx dt, which of course, as we know, is v sub x, v0 sub x, right? X, not y. Okay, v0 x. All right, so it's the velocity in the x direction. That's what this is. All right, that's the ke in the x direction, but of course, there's also kinetic energy in the y direction, 1/2 m y dot squared. Same idea. Y dot is v0y, right? v0y. Okay. So that's the kinetic energy. What about the potential energy? Well, remember from our picture, right? So we had, this is the y direction, this is the x direction, and our projectile, was here, going with a particular velocity, v naught, right, theta, okay? Its height above the ground is the potential energy, right? Well, it's related to the potential energy. So let's say it's right here at this point here. That's a distance y above the ground, right? So at here, it's going to be mgy is the potential energy, right? And we say that here that it's ke minus u, so this is going to be minus mgy, okay? And there's, oops, that was just the ke. That was just the ke. We need to put the Lagrangian down. Okay, let's put the whole Lagrangian down. L is equal to 1/2 mx dot squared plus 1/2 m y dot squared minus mgy. Okay, now Lagrange's equations, which are the equivalent, right, that get us to our equations of motion, look like this, and you might remember this. It's ddt of the partial derivative of L with respect to x dot. And actually, let's write this down in much more general terms. Q, so Q some variable, Q dot. Q could be x, y, or maybe you're in spherical coordinates, it could be r, theta, phi, right? Okay, it's a generalized coordinate minus the partial derivative of the Lagrangian with respect to that coordinate, not the dot of the coordinate, but that coordinate, is equal to 0. So this actually is a multiple set of equations. For us, it's only going to be 2 because I have 2 variables, x and y, right? I don't have, a z in this case. So really, this is 2 equations. So let's write it down for the x equation. Oh, sorry, just x. Okay. Let me erase that. Looks like a dot. Okay, so for the x direction. So first, we're going to take partial L, partial Q dot, and in this case, I'm going to write out the equations in terms of x, just to be really clear. So partial L, partial x dot, right, because we're using x now for Q, minus partial L, partial x equals 0. What does that get us? Well, partial L partial x dot is here, right? So we can, here's the only x dot we have, so that take the derivative of this, you're going to get, pull the 2 down, that cancels this 2, and you're just going to get m x dot, and remember I still have to take the time derivative, okay? And then minus partial L partial x. Well, there's no x, there's a y, but there's no x, okay? So that's just going to be 0. And what does that give us once I take the time derivative as long as m is constant? And that's it. In our problem, we should have stated m is constant. We have this be mx double dot equals 0. And if you go back in the video, you'll see that we actually wrote this down, right? Because remember, this x double dot is d squared x dt squared, okay? So we wrote this down. This is the differential equation for x, for the motion in x, okay? Let's do the y equation, okay? So now q is y, so d dt of partial L partial y dot minus partial L partial y is equal to 0. Okay, let's implement that. So the partial L partial y dot just gives us derivative here. So we have d dt of m y dot, right? We took the partial derivative here, and the 2 canceled, etc. And then we have this guy, partial L partial y, and we can see that there's a y here, so the partial derivative of L with respect to y is just minus mg, and then I have another minus sign here, so I get plus mg is equal to 0. And now rearranging, taking the time derivative here, I get my double dot plus mg equals 0. And I can cancel out these m's and bring the g to the other side, and I get y double dot is equal to minus g, which if you look back, you'll see we have the same thing. So this is d, remember that this is code for d squared y dt squared, right, this guy. So we got those equations of motions pretty darn quickly and without thinking about anything about forces. Now, of course, projectile motion is just super, super, super simple. And why would you need to go through all this? But this formulation is very powerful because it doesn't deal with vectors. And you can imagine in a complicated system, we've done problems in 341 where there was, you know, a particle going, or, you know, stuck to or inside of a cone, right? Like this kind of thing, like doing that with Newton's equations would just be awful, because think of all the forces you have to deal with, like the force of the cone on the particle and what direction that force points as the thing goes around. It's just difficult, very difficult to do with the Newton's equations, and very easy to do with Lagrangian dynamics, because all you have to do is figure out, you know what the kinetic energy is, right? That's easy. And you have to express the potential energy in terms of your coordinates, and you're good to go. Okay, give me 1 second here. Okay, so now we've seen sort of the basics of Lagrangian dynamics. Let's do the cone problem that I was mentioning to you. Okay, so let me get a new layer and we'll set it all up. Okay, here we go. All right, so we're going to look at a problem, and I'm going to get my pink here, that is a very classic problem. So you'll see this probably all over the place. I'm going to draw a coordinate system. This is the z-axis. This is the x-axis, and this is the y-axis. Okay. All right, so let's draw our cone. So terrible drawer, but I will try my best here. So we've got a cone. It's supposed to be centered on that z-axis. Sorry about that. And its vertex is down here at the origin. Okay. This cone has an opening angle here of alpha. And we have a particle that's just sitting on this cone. Not sitting on the cone, moving on the cone, but it can't leave the cone. Okay, so it's somehow given a little bit of a spin. You can imagine, right? If you could give us the particle a spin, it's going to stay on the cone, do what it's going to do. It's under the influence of gravity. It's the and of course all the forces that the cone is putting on it. So the two forces, the forces that are on it are the forces due to the cone, right? That are keeping it from flying off. And of course, the force of gravity straight down. Okay, so if you can imagine, if you were going to use Newton's second law, you'd have to tally up all the forces and you'd have to find all the vector components of all the forces acting on this due to the cone itself as it spins around and falls down, right? And you know, depending on how you initially spun it, right, it's going to do all kinds of different motions. So that's kind of hard. Certainly can be done, but it's not a happy problem. So let's look at how this is done in Lagrangian dynamics. Okay, let's get our pink color again. All right, so we have to decide on a coordinate system, and there's kind of a natural coordinate system for a cone, and that is the cylindrical polar. Sorry, brain not working. Okay, so we're gonna go out to here, and this will be rho. So right here is rho. Okay, and of course the distance up this part of the axis is z, right? Right, how far up the particle is z. And then there's, you know, if we drop this sort of line straight down to the xy axis, there's a projection of rho down here, and coming off the x-axis is the angle phi, okay? So as it sort of spins around on the cone, phi is going to be changing, the rho will be changing, z will be changing, but there's a constraint, right? Because there's a cone, there's a constraint on this system. And there's kind of two ways to treat this. In 341, we did look at constraint equations, like Lagrange multipliers to deal with constraints. We're not going to do that. We're just going to sort of build in the constraint. So if you think about what the constraint is telling you, it's telling you that rho and z are not independent, right? Because if they were independent, rho could be really, really big while z stayed the same, but obviously it can't be, right? So rho would be like way out here, while z stayed the same. That's not true because there's a cone, right, that it has to stay on. Okay, so if we look at some geometry here, we can see that sort of the opposite over adjacent here, right, is going to be rho over z, right? That's going to be tangent of that opening angle alpha. Okay, so that's kind of a constraint. Well, it is the constraint equation. It tells us that rho and z are not independent and that we don't really need to use one of them. So I'm going to pick, I like to use rho. I don't like to just use z. So I'm going to eliminate z and keep rho. Okay, so I'm going to write this over again as z equals rho cotangent of alpha. Okay, not too crazy. All right, now remember to do the Lagrangian, because we're going to do this with Lagrangian dynamics, we need the energies, right? So it's T or KE, that's for KE, right? KE minus U, the potential energy, okay? We need to construct this, and then we can use Lagrange's equations, which are d dt of partial L partial Q dot. Remember, Q dot's a stand-in for whatever coordinates you're using, minus partial L partial Q equals 0, okay? And then we can implement this. Well, first we have to write down Lagrangian. And often the hardest thing to write down is the KE, because you've got to like futz with your coordinate system and think about what to do. Well, all right, fine. It's not too hard because I can write down what is T. Well, in general, I know for sure that it's 1/2 m x dot squared plus y dot squared plus z dot squared. This is always a great starting place because most of the time, no matter what, sorry, it's a squared. No matter what coordinate system you're using, right, you know some transformation to get you from that coordinate system to Cartesian. So it's a nice place to start. This is always true, right? T is always this. And then if you're using some wacky coordinate system, as long as you know the transformation that goes from the wacky coordinate system to X, Y, Z, you can write down what T is. So that's where I always start. Okay. And this is also known as, of course, 1/2 m r dot squared, right? Because r dot is x in Cartesian, r dot, right? So let's go. So, and we can write this. I just want to point this out to you just to be really, really pedantic about my vector nature of things. This is r dot, the vector, dotted with itself, right? Where r dot in Cartesian only, right? This is the only, this only works in Cartesian because when you have other coordinates like spherical or cylindrical, polar, etc., elliptical coordinates, you have to worry about changing of the unit vectors. They change as well with time. But r dot in Cartesian is very simple. It's x dot times x hat plus y dot times y hat plus z dot times z hat. So really I'm starting from this equation or this equation here, right? That's what I'm starting from. But I've written it out in Cartesian. But in Cartesian, it's very, very simple. So if you dotted r with itself, you get x dot squared plus y dot squared plus z dot squared, right? Okay. So now we just got to figure out what are these wacky coordinates in terms of Cartesian. Well, that's easy. We know that. So I'm going to write down x. You know, these are the usual cylindrical polar equations. So x is rho cosine of phi. Y is rho sine of phi. And z is usually just z, right, in cylindrical polar, right? There's no change. But here we have that constraint that tells us that it's rho cotangent of, not cosine, cotangent of alpha. Okay, that's our constraint equation. Okay, so now we just need to take derivatives. And you just got to be a little careful, fun times, derivative, right? So let's do x dot. So x dot is rho dot, right, cosine of phi, and now by product rule plus rho cosine, not plus, because we got to take the derivative of a cosine, and that's a negative sign, minus sine of phi, because remember phi is also changing, right, times phi dot. Okay, so we remember this is just chain rule that I've used product rule and then chain rule for this, yeah? Okay. And when you're doing a problem like this, you have to think about what's changing and what's not. Well, clearly, rho can change and phi can change, right? And of course, z can change, but it's constrained by this equation. So sometimes you won't have to take derivatives of everything in there because those things aren't changing. But in this case, we've got everything, phi and rho are changing. All right, let's take y dot. Y dot is a rho dot sine of phi, and then plus rho cosine phi, phi dot. Okay? And z is really easy because the alpha is not changing. That's just a property of the cone itself. So we have rho dot cotangent of alpha. Okay? Great. Now we have to square it all. C squared. Okay, so t equals 1/2 m, and now I'm going to square everything. All right, let's square x dot, rho dot squared cosine squared phi plus rho squared sine squared phi dot squared minus 2 rho dot rho cosine phi sine phi dot. Okay, that's that x dot squared. Now for y dot squared. Okay, similar thing. Plus rho dot squared sine squared phi, sorry, plus rho squared cosine squared phi dot squared. And I'm going a little off to the side here. Sorry about that. Okay. And then plus 2 rho dot rho cosine phi sine phi dot. And then plus z dot squared, sorry, rho dot squared cotangent alpha. Okay. Now, at this point, you might be tempted to just stick this into, calculate your u, stick it all into, start cranking through these guys, right? But I encourage you to simplify your Lagrangian as much as is humanly possible, okay? Spend the time to simplify your Lagrangian, and this kinetic energy part is pretty long and nasty. Simplify, because when you start applying the equations, you're going to get yourself into a lot of algebra trouble. Okay, So let's go and see what we can do. It looks good actually. I love it when I have my cosine squareds and sine squareds. That's awesome. So look at this one. We have a rho dot squared cosine squared and a rho dot squared sine squared. Woohoo, that's going to go to just rho dot squared. Rho dot squared. Okay. And then we have this one, rho dot phi dot squared. Rho squared phi dot squared. Another rho squared phi dot squared with a sine squared plus cosine. Because remember, sine squared plus cosine squared is 1. So that's going to go and become plus rho squared phi dot squared. Okay. These two cancel out completely. Yay. And then we have plus rho dot squared cotangent squared alpha. And then I can even combine these two guys because 1 plus cotangent squared is cosecant squared. So if you don't remember that, just, prove it to yourself. Okay, 1/2 m, and then we have rho dot squared cosecant squared alpha plus rho squared phi dot squared. Now that looks a whole lot better than before. Okay, it's much better. So and all we have to do is now figure out what u is. So what is u? Well, of course, it's mgz, right? So it's how far above the plane you are, because that's gravity, right? So it's the gravitational potential energy. We don't have any other potential energies, no springs or anything. And z, of course, is rho cotangent alpha, and we're good to go. So let's write down Lagrangian. I'm going to put that in a yellow color. So the Lagrangian, finally, 1/2 m rho dot squared cosecant squared alpha plus 1/2 m rho squared phi dot squared, and then minus my potential energy. Now, I made a choice here, by the way, of where the potential energy is 0. So I said U equals 0 here, right? You always have to make that choice. I didn't write it down, but you're always making that. I'm always making that choice. Sometimes I don't make it explicit like that, but that's what I'm doing. Okay, so minus mg, oops, that's supposed to be yellow, mg rho cotangent of alpha. There's our Lagrangian, yay. All right, now we are going to do, remember, this is a set of equations. There's no way around that. And the first coordinate that I have, my q's, right? So my q's, oh, that's not a q. Q's are rho and phi. Okay, so I'm going to start my phi equation here. Oh, sorry, rho equation. All right, so, okay, so rho, I like to do it with this little colon here to say I'm doing the rho equation now. I'm going to do that in blue. Okay, so actually let's make this blue too. Ooh, that's kind of pretty. All right. All right, so let's implement. So I'm going to write it down. Now it's Lagrange's equations for rho are d dt of partial L partial rho dot minus partial L partial rho equals 0. So let's do it. Okay, so now we are implementing the rho equation, right? So let's start with the partial L partial rho dot. So what do we got? That just has, this is just this term, there's no other rho dots anywhere. So let's do that. So we're gonna write down ddt, oops, wrong color. Let's get rid of that and get back to our blue. Okay, blue, all right, so ddt, and then the partial L partial rho dot, the 2 comes down and cancels that 2, and we just get m rho dot cosecant squared alpha. And then this minus partial L partial rho. Notice there's 2 terms, this one and this one, that have a rho in it. So let's do the first one. So minus m rho phi dot squared. and then here plus mg cotangent alpha. Okay, great. And now we're just going to implement this. The only thing that changes with time is the rho dot. These two things are constant. And so we end up with, oh, this whole thing is equal to 0. So we end up with m rho double dot cotangent alpha minus m rho phi dot squared plus mg cotangent alpha equals 0. Okay, so if we solve for rho dot here, which is kind of standard, first we can get rid of all these m's, they all cancel, and so what do we get for our rho dot? So our differential equation is, let's see, plus rho phi dot squared, and then minus g cotangent alpha all over, and I think I wrote cotangent, that's supposed to be a cosecant, squared. Okay. Sorry about that. Okay, over cosecant squared alpha. Okay, that looks a little gnarly, but we certainly can, you know, put that into a computer and solve. The only thing is it's now coupled with this phi dot equation. So let's go to phi dot and see how that equation turns out. All right, let's get an orange for that. So phi. Okay, writing down the Lagrange's equations for phi. Partial phi dot now, right? And then minus partial L partial phi equals 0. All right, so let's do this one, partial L partial phi dot. That's only this term. Okay, so we get the 2 cancels this 2. We get ddt of m rho squared phi dot. And then there is no phi's anywhere for the partial L partial phi. There's literally no phi's. So that means that this whole thing is just 0. Now this is kind of special because this tells us something is conserved, right? It says whatever's in here is conserved. Well, let me remind you that the angular momentum in term is I omega, right? This is the angular velocity, which we could write as I phi dot, right? Because phi dot is the velocity in phi. And then I for just a particle going around a circle is just m times the radius squared, which is rho squared phi dot. So this is just telling us that the angular momentum is conserved. Okay, so that means that this m, and we can replace this whole thing, right? So this is saying that m rho squared phi dot is equal to a constant, and we can just call that L, okay? And so now you can see here that you could replace your phi dot squared with L. So in other words, I can write phi dot is L over m rho squared, and phi dot squared is L squared over m rho squared, right? So now I could put that in here, and this is a constant, this isn't obviously, and I could go through and calculate, put this into a computer or whatever I need to do to find rho of t, okay? All right, so this is, remember that once we get to the differential equation stage, right, like this, we are done, because again, you can either solve it on paper or you can stick it into a computer. But I challenge you to go try to do this problem with just forces. I mean, you know, yeah, there's a lot of algebra here, but I didn't have to think a lot. It was just kind of turning a crank. Okay. So sometimes that's advantageous. Okay. All right. Well, good luck. And remember that you have a homework due on 341 work by next Friday. Okay.